For centuries, space exploration has been driven by human curiosity, courage, and ingenuity. From the first telescopes that revealed distant planets to the rockets that carried astronauts beyond Earth's atmosphere, every leap forward depended on human decision-making. But as we venture farther into the cosmos, beyond the moon, beyond Mars, and into environments too distant, dangerous, or complex for direct human control, a new explorer has emerged. Artificial intelligence is no longer just a supporting tool. It is becoming the mind behind the mission. In space, decisions often must be made millions or even billions of kilometers away from Earth. Signals traveling at the speed of light can take minutes, hours, or even days to reach their destination. A rover on Mars cannot wait for instructions when its wheels slip on unstable terrain. A spacecraft passing through the intense radiation belts of Jupiter cannot pause for human confirmation when systems begin to fail. In these moments, artificial intelligence acts as the spacecraft's brain, observing, analyzing, predicting, and acting autonomously. AI in space exploration begins with perception. Space is an environment saturated with data, images, radiation measurements, temperature fluctuations, magnetic fields, chemical signatures, and countless other signals. Human operators cannot realistically process all of this information in real time. Machine learning algorithms, however, thrive on complexity. They can identify patterns invisible to the human eye, distinguish meaningful signals from cosmic noise, and adapt their understanding as conditions change. What once took teams of scientists months to analyze can now be achieved in moments. One of the earliest and most critical roles of AI in space missions is navigation. Spacecraft must calculate trajectories with extreme precision, often adjusting their paths mid-flight to account for gravitational influences, fuel constraints, and unexpected obstacles. AI-driven navigation systems continuously evaluate sensor data and predict future positions, enabling spacecraft to make autonomous corrections. This capability has transformed deep space missions, allowing probes to operate independently for years without constant guidance from Earth. On planetary surfaces, artificial intelligence becomes even more essential. Rovers exploring Mars, for example, operate in harsh, unpredictable environments. Dust storms can block sunlight, temperatures can drop to lethal extremes, and the terrain itself can trap or damage robotic explorers. AI allows these machines to assess their surroundings, choose safe paths, avoid hazards, and prioritize scientific targets. Instead of following rigid, pre-programmed commands, modern rovers can reason about their environment and adapt their behavior accordingly. Scientific discovery itself is increasingly shaped by AI. Space missions generate far more data than scientists can manually examine. AI systems are trained to scan astronomical images for anomalies, new stars, distant galaxies, exoplanet transits, or sudden cosmic events. These systems do not replace human astronomers. Instead, they act as intelligent collaborators, highlighting the most promising findings and allowing scientists to focus their expertise where it matters most. In many cases, AI has already discovered celestial phenomena that might otherwise have remained unnoticed. Artificial intelligence also plays a vital role in spacecraft health and survival. Spacecraft are complex systems with thousands of components, each subject to wear, radiation damage, and unexpected failure. AI-driven monitoring systems continuously analyze telemetry data, detecting subtle signs of malfunction long before they become catastrophic. These systems can diagnose problems, recommend corrective actions, and in some cases, execute repairs autonomously. This capability dramatically increases mission longevity and reduces the risk of total failure. As humanity pushes toward long-duration missions to Mars, asteroids, and eventually interstellar space, AI becomes not just useful, but essential. Astronauts cannot rely on Earth-based support when communication delays stretch into tens of minutes. Intelligent onboard systems will manage life support, optimize energy usage, schedule tasks, and respond to emergencies. In effect, AI becomes a silent crew member, constantly vigilant, tirelessly analytical, and always ready to act. The integration of artificial intelligence into space exploration marks a profound shift in how humanity explores the universe. We're no longer sending machines that merely obey commands. We are sending explorers that can think, learn, and evolve. As we stand at the threshold of a new era in space discovery, AI is not just helping us reach the stars, it is redefining what it means to explore them. As space missions grow more ambitious, the challenge is no longer simply reaching distant worlds, but surviving and operating within them for years, sometimes decades, without direct human control. This is where artificial intelligence becomes the true architect of deep space autonomy. Beyond navigation and perception, AI now governs decision-making, mission planning, and real-time adaptation in environments where human intervention is impractical or impossible. In traditional space missions, every major decision was planned years in advance on Earth. Engineers anticipated scenarios, wrote detailed command sequences, and uploaded them to spacecraft long before launch. While this approach worked for short missions near Earth, it becomes dangerously limiting in deep space. Unknown variables are inevitable. Unexpected terrain, unpredicted radiation spikes, equipment degradation, or entirely new scientific opportunities. Artificial intelligence enables spacecraft to respond intelligently rather than rigidly. Autonomous mission planning allows AI systems to evaluate goals, constraints, and available resources simultaneously. A spacecraft must constantly balance power consumption, thermal stability, communication windows, and scientific objectives. AI-driven planners can reschedule activities on the fly, deciding whether to conserve energy during a dust storm, prioritize critical observations, or delay non-essential tasks. These systems weigh trade-offs with a level of speed and precision unattainable by human operators working across vast distances. One of the most powerful aspects of AI in space exploration is its ability to learn from experience. Machine learning models onboard spacecraft adapt over time, refining their understanding of local conditions. A rover traversing a planetary surface gradually improves its ability to recognize safe terrain, identify scientifically valuable rock formations, and estimate risks. Instead of relying solely on pre-launch training data, the AI evolves based on real-world exposure, becoming more capable as the mission progresses. Decision-making under uncertainty is a defining challenge of space exploration. Spacecraft often operate with incomplete information, limited sensor coverage, and unpredictable environmental changes. AI systems are designed to function within these constraints, using probabilistic reasoning to assess potential outcomes. Rather than seeking perfect information, they determine the most rational action given what is known. This approach mirrors human intuition, but with far greater computational depth and consistency. Communication delays further reinforce the necessity of intelligent autonomy. When a spacecraft near Mars sends data to Earth, it may take up to 20 minutes to receive a response. During that time, conditions on the ground may already have changed. AI enables local decision-making, ensuring immediate responses to hazards such as mechanical strain, unstable slopes, or sudden system anomalies. This capability has already prevented mission-ending failures. By allowing spacecraft to protect themselves without waiting for human approval, artificial intelligence also transforms how missions prioritize discovery. Instead of following a fixed list of targets, AI systems evaluate incoming data to determine what is most scientifically significant. If an unexpected chemical signature appears, or an unusual geological structure is detected, the AI can adjust the mission plan to investigate further. This dynamic approach maximizes scientific return and allows missions to capitalize on discoveries that were never anticipated during initial planning. Beyond individual spacecraft, AI coordinates entire mission architectures. Swarms of satellites, autonomous probes, and surface robots can operate as collaborative networks, sharing data and dividing tasks intelligently. AI manages this distributed intelligence, ensuring efficient coverage, redundancy, and resilience. If one unit fails, others adapt to compensate, preserving the mission's overall objectives. As humanity prepares for crewed missions beyond low Earth orbit, AI-driven decision support becomes a critical safety system. Intelligent onboard systems assist astronauts by monitoring environmental conditions, predicting system failures, and recommending actions during emergencies. In extreme situations, AI may even take control to prevent catastrophic outcomes, acting faster than human reflexes in life-threatening scenarios. The evolution of AI-powered autonomy marks a turning point in space exploration philosophy. We are transitioning from micromanaged missions to self-directed explorers capable of independent judgment. This shift does not diminish human involvement. Instead, it elevates it. Scientists and engineers move from constant operators to strategic partners, guiding intelligent machines that extend human presence far beyond Earth. In this partnership between human curiosity and artificial intelligence, the boundaries of exploration expand into realms once thought unreachable. As artificial intelligence takes on greater responsibility in space exploration, its role in scientific analysis becomes increasingly profound. Space is not just vast, it is overwhelmingly rich in data. Every telescope, probe, rover, and satellite continuously streams information back to Earth, generating datasets so enormous that traditional methods of analysis struggle to keep pace. Artificial intelligence bridges this gap, transforming raw cosmic data into meaningful knowledge and accelerating discovery across the universe. Modern space telescopes capture millions of images and spectra, each containing subtle clues about distant stars, galaxies, and planets. AI algorithms trained on astronomical data can rapidly scan these observations, identifying patterns that indicate new phenomena. Exoplanets, for example, reveal themselves through tiny dips in a star's brightness as they pass in front of it. These signals are often buried in noise caused by stellar activity or instrumental variation. Machine learning models excel at separating genuine planetary signatures from false positives, enabling the discovery of worlds that might otherwise remain hidden. Beyond detection, AI contributes to interpretation. Understanding the composition of planetary atmospheres, the structure of galaxies, or the behavior of black holes requires analyzing complex, multidimensional datasets. AI systems can correlate variables across vast parameter spaces, revealing relationships that human researchers may not immediately recognize. These insights guide scientists toward new hypotheses and deepen our understanding of cosmic processes that operate on scales far beyond everyday experience. Artificial intelligence also plays a crucial role in time-sensitive discoveries. Some cosmic events, such as supernovae, gamma-ray bursts, or gravitational wave signals, occur suddenly and fade quickly. AI-driven monitoring systems continuously scan the sky, instantly flagging unusual activity. When an event is detected, alerts are sent to observatories around the world, allowing telescopes to pivot and observe the phenomenon in real time. This rapid response dramatically increases the scientific value of transient events, capturing details that were previously missed. On planetary missions, AI acts as an intelligent field scientist. Rovers equipped with AI-based vision systems analyze images of rocks, soil, and terrain, selecting the most promising samples for closer inspection. Instead of sending every image back to Earth for review, the rover prioritizes data, focusing on features most likely to yield scientific breakthroughs. This selective attention is essential when bandwidth and power are limited, ensuring that the most valuable information reaches researchers. AI's contribution extends to simulation and modeling, which are foundational to space science. Many cosmic phenomena cannot be directly observed in detail, such as the internal dynamics of stars or the formation of galaxies over billions of years. AI-enhanced simulations process enormous amounts of data to recreate these processes virtually, testing theories under a wide range of conditions. By comparing simulated outcomes with real observations, scientists refine their understanding of the universe's underlying laws. Machine learning also assists in anomaly detection, identifying observations that do not fit existing models. These anomalies are often the most scientifically exciting, hinting at unknown physics or entirely new classes of objects. AI systems trained to recognize normal patterns can immediately highlight deviations, drawing attention to potential discoveries. In this way, AI does not just confirm what we know. It actively challenges assumptions and expands the frontier of knowledge. Artificial intelligence further democratizes space science by enabling collaboration at an unprecedented scale. Researchers across the globe can access AI tools that analyze shared datasets, reducing barriers to participation and fostering diverse perspectives. Automated data processing pipelines allow scientists to focus on interpretation and theory rather than manual sorting and cleaning of data. This shift accelerates the pace of discovery and encourages innovation across disciplines. As future missions venture deeper into space, AI will increasingly operate without real-time human oversight, conducting experiments, analyzing results, and adapting strategies independently. A probe exploring the icy moons of the outer solar system may decide which subsurface samples to study, while an interstellar observatory may autonomously adjust its instruments to investigate unexpected signals. In these scenarios, AI becomes not just an assistant, but a scientific agent in its own right. The integration of artificial intelligence into scientific exploration reshapes humanity's relationship with the cosmos. We are no longer limited by human attention, speed, or perception. Through AI, our curiosity gains a powerful extension, one capable of observing the universe continuously, interpreting its complexity, and revealing its secrets with unprecedented depth. As machines learn to read the language of the stars, humanity moves closer to understanding its place within the vast cosmic narrative. As artificial intelligence becomes deeply embedded in space exploration, its influence extends beyond discovery and analysis into the realm of survival, sustainability, and long-term presence beyond Earth. Space is an unforgiving environment where even minor failures can escalate into mission-ending disasters. AI-driven systems are increasingly responsible for ensuring that spacecraft, habitats, and human crews can endure these extreme conditions over extended periods of time. One of the most critical applications of AI in space is predictive maintenance. Spacecraft operate under constant stress from radiation, temperature extremes, micrometeoroid impacts, and mechanical wear. Traditional monitoring systems rely on predefined thresholds, triggering alerts only after a parameter crosses a danger limit. Artificial intelligence, however, detects subtle trends and correlations within telemetry data, identifying early warning signs of failure long before they become critical. By predicting component degradation in advance, AI enables preventative action that preserves mission integrity. In crewed missions, AI becomes an essential guardian of life support systems. Maintaining breathable air, clean water, stable pressure, and safe temperatures requires continuous regulation and rapid response to anomalies. AI systems monitor thousands of variables simultaneously, balancing resource usage while adapting to changing crew activities and environmental conditions. In emergencies, AI can isolate failing subsystems, reroute resources, and stabilize conditions within seconds, actions that may be impossible for human crews under stress. Artificial intelligence also supports human performance and well-being in space. Long-duration missions expose astronauts to isolation, confinement, and psychological strain. AI-driven systems analyze behavioral patterns, speech, and physiological data to detect signs of fatigue, stress, or declining cognitive function. By providing early warnings and adaptive support, such as workload adjustments or environmental changes, AI helps protect mental and emotional health, which is as critical as physical survival in deep space. As humanity prepares for sustained operations on the Moon and Mars, AI becomes central to habitat management and infrastructure development. Autonomous construction systems guided by AI can assemble structures, deploy solar arrays, and prepare landing zones before human arrival. These systems operate continuously, optimizing workflows and adapting to unexpected conditions such as uneven terrain or material limitations. By the time astronauts arrive, AI-enabled machines may have already built the foundations of off-world settlements. Resource utilization represents another transformative role of AI. Transporting supplies from Earth is expensive and limited, making local resource extraction essential for long-term exploration. AI systems analyze geological data to identify locations rich in water ice, minerals, or other usable materials. Once extraction begins, AI optimizes processing methods, manages energy consumption, and ensures sustainable use. This intelligent resource management is a cornerstone of future space economies and permanent human presence beyond Earth. Artificial intelligence further enhances resilience through redundancy and adaptability. In complex space systems, failures are inevitable. AI coordinates backup systems, reallocates tasks, and modifies mission plans to compensate for lost capabilities. This adaptability allows missions to continue even after significant setbacks, transforming potential failures into survivable challenges rather than catastrophic ends. Human-AI collaboration is especially critical during exploration of hazardous environments. On planetary surfaces with toxic atmospheres, extreme radiation, or unstable terrain, AI-controlled robots act as extensions of human explorers. These machines scout dangerous areas, conduct experiments, and relay information in real time. Humans, in turn, provide strategic judgment and creativity, guiding AI systems toward meaningful objectives. This partnership amplifies human capability while minimizing risk. As missions venture farther from Earth, communication delays increase, making autonomy not just advantageous but mandatory. AI-driven systems manage daily operations without constant supervision, making decisions that directly affect survival and success. Trust in these systems becomes essential, requiring rigorous testing, transparency, and ethical design. Engineers must ensure that AI behaves predictably while remaining flexible enough to handle the unknown. The integration of artificial intelligence into survival and sustainability efforts represents a shift in how humanity approaches space exploration. Instead of brief visits and isolated missions, AI enables continuity, long-term habitation, ongoing scientific study, and a gradual expansion of human presence into the solar system. Through intelligent systems that protect, adapt, and endure, humanity moves from exploration to establishment, laying the groundwork for a future among the stars. As artificial intelligence assumes a central role in space exploration, it also reshapes how humanity prepares for the most ambitious journeys ever imagined. Missions that extend beyond Mars, beyond the outer planets, and ultimately beyond the boundaries of our solar system. In these extreme frontiers, AI is not merely a system embedded within spacecraft. It becomes the driving force that enables exploration itself to exist. Interplanetary and interstellar missions demand endurance on timescales far exceeding human lifespans. Spacecraft traveling for decades must function without maintenance, updates, or direct intervention from Earth. Artificial intelligence provides the continuity required for such missions, managing evolving system behavior across years of exposure to radiation, vacuum, and mechanical fatigue. AI systems learn how their own spacecraft changes over time, adjusting operations to preserve functionality long after launch. One of the most profound contributions of AI lies in adaptive exploration strategies. Unlike missions confined to predefined objectives, future explorers must respond to discoveries as they occur. An AI-guided probe traveling through the outer solar system may encounter unexpected magnetic fields, unusual particle distributions, or unknown celestial bodies. Instead of simply recording data, the AI evaluates scientific relevance, modifies observation priorities, and reallocates resources to investigate the most significant findings. Exploration becomes dynamic rather than scripted. Artificial intelligence also plays a critical role in propulsion and energy optimization. Deep space missions rely on limited fuel and power sources, such as nuclear generators or advanced solar systems operating far from the sun. AI algorithms continuously analyze energy usage, predicting future demands and optimizing thrust, communication, and scientific operations accordingly. By maximizing efficiency, AI extends mission lifetimes and expands the reachable boundaries of space. In the context of interstellar exploration, AI becomes the surrogate for human presence. Probes sent to nearby star systems cannot rely on instructions from Earth due to communication delays spanning years. These spacecraft must interpret alien environments, analyze unfamiliar physics, and make independent judgments. AI systems designed for such missions are trained not just to follow rules, but to reason under complete uncertainty. They represent humanity's curiosity embodied in machine form, exploring regions no human may ever physically reach. Artificial intelligence further transforms how data from distant missions is understood. As spacecraft send back compressed and prioritized information, AI systems on Earth collaborate with onboard intelligence to reconstruct context, identify patterns, and refine models of distant environments. This distributed intelligence, spanning millions of kilometers, creates a unified cognitive system that bridges the gap between Earth and the stars. Ethical considerations become increasingly important as AI gains autonomy in space. Decisions made by intelligent systems can determine the success or failure of missions worth billions of dollars, and in crude scenarios, the survival of human lives. Engineers must define boundaries, values, and safeguards that guide AI behavior in unforeseen situations. This includes ensuring transparency in decision-making and maintaining human oversight at the highest strategic levels, even when real-time control is impossible. AI also shapes the future of space exploration by accelerating innovation on Earth. Technologies developed for autonomous space systems, advanced robotics, machine learning, energy optimization, and resilience engineering feed back into terrestrial applications. In this way, space-focused AI research drives progress across medicine, climate science, transportation, and global infrastructure, reinforcing the mutual relationship between space exploration and human advancement. As artificial intelligence continues to evolve, the distinction between machine tool and exploratory partner begins to blur. Future AI systems may generate hypotheses, design experiments, and even propose new missions based on accumulated knowledge. Rather than waiting for human direction, these systems could actively suggest where to explore next and why. Exploration becomes a dialogue between human imagination and artificial reasoning. In embracing AI as a central force in space exploration, humanity extends its reach beyond biological limitations. Machines do not tire, age, or fear the unknown. Guided by human purpose and curiosity, artificial intelligence becomes the vessel through which civilization reaches deeper into the cosmos. Each autonomous decision, each adaptive response, and each discovery made by AI-driven explorers carries humanity's desire to understand the universe, projected across distances that once defined the limits of possibility. As humanity stands at the edge of a new cosmic era, artificial intelligence emerges not simply as a technology, but as a defining force shaping the future of space exploration. The journey that began with simple automated systems has evolved into a profound partnership between human intelligence and machine cognition. In this final stage of the narrative, AI is no longer viewed as a tool operating in the background, but as an essential participant in humanity's expansion into the universe. The future of space exploration will be characterized by complexity far beyond anything previously attempted. Multi-planet missions, autonomous space stations, self-repairing spacecraft, and vast networks of probes will operate simultaneously across the solar system. Coordinating such an intricate ecosystem is impossible without advanced artificial intelligence. AI will manage traffic in orbital space, allocate communication bandwidth, and synchronize scientific objectives across countless platforms. Space will become an interconnected environment, governed by intelligent systems that ensure order, efficiency, and safety. Artificial intelligence will also redefine exploration timelines. Traditional missions are constrained by human planning cycles and limited operational windows. AI-driven exploration, by contrast, operates continuously. Autonomous observatories will monitor the universe without interruption, detecting subtle changes over decades. Planetary explorers will persist through seasonal cycles, adapting their behavior as environments evolve. This continuity transforms exploration from isolated missions into ongoing presence, allowing humanity to observe long-term processes that were once inaccessible. One of the most transformative impacts of AI lies in enabling the search for life beyond Earth. Identifying biosignatures, chemical or physical indicators of life, requires analyzing vast and complex datasets. AI systems can recognize patterns associated with biological activity, even when those patterns differ from life as we know it. This ability expands the search beyond Earth-like conditions, increasing the likelihood of discovering unfamiliar forms of life in the cosmos. In this context, AI becomes a critical interpreter of alien environments, translating unknown signals into meaningful insights. As human settlements extend beyond Earth, artificial intelligence will govern entire ecosystems. Lunar bases, Martian habitats, and deep space stations will rely on AI to balance resources, manage waste, regulate climate, and maintain structural integrity. These systems must function reliably for years with minimal human intervention. AI enables sustainability in environments where error margins are vanishingly small and recovery options are limited. Education and knowledge transfer will also evolve through AI-powered exploration. Intelligent systems will curate and contextualize the vast flow of information generated by space missions, transforming raw data into accessible understanding. Scientists, students, and the public will engage with dynamic representations of the universe, guided by AI interpreters that adapt explanations to different levels of expertise. In this way, space exploration becomes a shared human experience rather than a distant scientific endeavor. The philosophical implications of AI in space are profound. As machines make discoveries, interpret cosmic phenomena, and operate independently for generations, they carry fragments of human intention far beyond our physical reach. These systems represent humanity's values, curiosity, and desire for meaning encoded into artificial minds. The question is no longer whether machines can explore space, but what it means for humanity when they do so on our behalf. Despite its autonomy, artificial intelligence does not replace the human spirit of exploration. Instead, it amplifies it. Humans provide vision, purpose, and ethical direction. AI provides endurance, precision, and adaptability. Together, they form a symbiotic relationship that overcomes the limitations of distance, time, and environment. This partnership allows humanity to dream bigger, explore farther, and understand more deeply than ever before. Looking forward, the legacy of AI-driven space exploration will be measured not only by discoveries made, but by perspectives gained. By extending our senses and intellect into the cosmos, AI helps humanity see itself from a broader vantage point. Earth becomes one world among many, fragile yet extraordinary, connected to a universe vast beyond comprehension. In the end, artificial intelligence serves as both a mirror and a bridge. It reflects human ingenuity while bridging the gap between what we are and what we aspire to become. As AI-guided explorers travel into the darkness between stars, they carry with them humanity's oldest question, what lies beyond, and our newest answer, a future where intelligence, both human and artificial, explores the universe together. As the story of artificial intelligence in space exploration reaches its closing chapter, one truth becomes clear. AI is not a passing enhancement, but a permanent extension of humanity's presence in the universe. What began as algorithms assisting navigation and data processing has evolved into intelligent systems capable of independent reasoning, long-term adaptation, and discovery far beyond human reach. Through AI, exploration is no longer limited by human lifespan, physical endurance, or proximity to Earth. In the years ahead, the boundary between exploration and stewardship will grow increasingly important. AI-guided systems will not only explore distant worlds, but also protect them, ensuring responsible interaction with environments that may harbor fragile ecosystems or undiscovered forms of life. Ethical exploration, minimizing contamination, preserving scientific integrity, and respecting the unknown will depend heavily on intelligent systems that can enforce these principles autonomously. Artificial intelligence also reshapes how humanity measures success in space. Achievement is no longer defined solely by flags planted or footprints left behind, but by sustained understanding, continuous observation, and long-term coexistence with the cosmic environment. AI enables missions that evolve over generations, gathering knowledge slowly and deliberately, building a cumulative understanding of the universe that transcends individual human lifetimes. Perhaps most importantly, AI-driven exploration changes how humanity sees itself. As intelligent machines carry our questions into deep space, they act as emissaries of human thought, curiosity, and imagination. Each autonomous decision made by a distant probe reflects choices designed on Earth, connecting human intention with cosmic discovery. In this sense, AI becomes a storyteller of humanity's journey, recording our desire to understand the unknown. The universe remains vast, silent, and indifferent, yet through artificial intelligence, humanity gains the ability to listen more closely than ever before. We extend our senses into darkness, our reasoning into complexity, and our presence into regions once unreachable. AI does not diminish the human role in exploration. It magnifies it, allowing a small species on a pale blue planet to engage meaningfully with the cosmos. As the discussion closes, the path forward is clear. Human curiosity sets the direction, artificial intelligence carries the momentum, and the universe provides the challenge. Together, they form a narrative of exploration that has only just begun, one where intelligence, in all its forms, reaches outward, seeking understanding among the stars.